Okay, good morning, Year 12. What we're going to have a look at today is 6E, applications of integration of trig functions. But before we do that, I just wanted to have a quick look at some of our trig identities that may have come up in your last exercise and may help you out a little bit today as well. Okay, so this first blue trig identity here that says sine squared x plus cos squared x is equal to 1 is something that's really important, and you learned that earlier on in year 11, which was about a year ago, and you still need to know these. So this is the one that I need you to remember, and the other ones we can work out from that. Okay, so sine squared of theta or plus cos squared of theta is 1, or sine squared x plus cos squared x is 1. This is not given to you on your HSC formula sheet. I'm going to call that equation 1. So what I want to do is divide equation 1 by sine squared x. Just the first thing that's in there. So I'm going to have sine squared x divided by sine squared x. I'm going to have cos squared x divided by sine squared x. And then 1 divided by sine squared x. And in doing this, we actually are deriving our second formula for trig identities. So this first part, sine squared x over sine squared x becomes 1. Cos squared x on sine squared x becomes cot squared x. So the same rules are happening here in terms of ignoring the squared. So cos on sine is cot, so cos squared x on sine squared x is cot squared x. And so we know 1 on sine is cosec, so 1 on sine squared x is cosec squared x. And that's our second trig identity equation. I recommend not memorizing it, but working out the way that we just did, because I think there's a lot of room for error if we need to memorize it. And the third trig identity, what we do is we go back to our first one. So again, we're just remembering this one here. And we're going to divide that now by cos squared x. So I get sine squared x divided by cos squared x. And I get this identity, which is tan squared x. I then go cos squared x divided by cos squared x, which is 1. So I've got tan squared x plus 1. And my last part here on the other side of the equal sign is 1 divided by cos squared x, which is sec squared x. And that's our third trig identity equation. Now this third one here is really important in this exercise and our last one, because we're integrating sec squared x, and we could actually be given this thing here, tan squared x plus 1, and we might need to then make that into sec squared x. So there's a few little manipulations that we might need to do along the way. That may help us out a little bit, but I'm going to move over to our work for today now. So back to our notes, we're going to recall that if a function f of x is above another function g of x for some interval within the x values, then the area between the curves is given by this formula. The integral between those two values that we're looking at, and it's the first curve or the top curve minus the bottom curve. We looked at that a lot. This is still going to apply in this section, and you will need to understand that throughout the rest of the course. Okay, let's have a look at our first question. The first one is saying sketch the curve y equals cos x over 2 in the interval 0 is less than x is less than 4 pi. So we're going to do that first. That's the first thing. And then we're going to find the area enclosed by the function. Okay, so what we want to first think of is this curve, y equals cos x on 2. Now I'm going to move over here a little bit. We've got, oops, we'll just change pen colour. Y equals cos x on 2, and that's very similar to y equals cos of x, which we know. We're familiar with cos of x. We looked at it last year quite a fair bit, and we know that we have a period of that curve being 2 pi. So that curve repeats itself every 2 pi. That's our x, that's our y. Cos starts at 1. I'm going to go around here like this. Just a quick sketch of this curve, and that would be 2 pi. That would be our 0. We would have pi in there, pi on 2, and 3 pi on 2. So remembering the period is the time that it takes for the curve to go from my first point back to the point in exactly the same spot up here, which would be that point. So the period of cos of x is 2 pi. I'm just going to scroll down here. This part here in this little box comes from your year 11 book. And it talks about the periods of sine, cos, and tan. But what we did is we popped letters in front of the whole function, and we popped letters in front of our x. So if you have a look over here, if y is equal to a cos b of x, it has a period of 2 pi over b. So what we actually have over here, our curve is y equals cos of a half x. And we're going to relate it back to cos x by getting our period from cos x, which was 2 pi, and dividing it by b. Remember, in this little formula that we learned last year, b was the number in front of the x. I have a number in front of the x here being a half, so I'm going to divide my 2 pi by a half. Now, you need to be very careful here, because what a lot of people are going to do, they're going to just divide my 2 pi by 2. But I'd only be doing that if I had 2x. In this case, I have a half x. And if I'm dividing something by a half, I am multiplying by its reciprocal. So I'm multiplying by 2 over 1, and I'm going to end up with 4 pi. And 4 pi is the period, let's write that in a sentence, is the period of y equals cos of a half x, which is y equals cos x on 2. So that's how we change between one period and the other. So that's our period, and that actually works really well when we look at that, because what we're looking at with our curve here in the question, it's getting us to sketch that curve in the interval between 0 and 4 pi. So we're looking at one period or one cycle of that curve. So I've drawn a quick sketch of that down here. There we go. Here's my cos x on 2. It starts at 1 still, and it has a period of 4 pi, so it repeats every 4 pi. But if you're interested, and it's probably a really good thing to look at, if I have a look back here at my cos of x, if I just quickly fix up that graph so it goes a little bit longer there, if I was to draw my cos x on 2 in, and we might pop that in another colour, and go y equals cos x on 2. It has a period of 4 pi, so I'm going to be starting up here. I'm going to be finishing down here. So I'm going to be moving through my curve like that. So that's the difference between the two curves, the pink one being cos of x and my purple one being cos of x on 2. So similarly, if we had cos 2x, it's going to not stretch it out, it's going to condense it, and we'd have it happening in a lot smaller period, and it happened in pi. Let's go back to our question. Okay, so we've nearly finished the first part. It says sketch the curve cos x on 2 in this interval. Here's my curve, and I'm going to find the area enclosed by the functions. Now I want you to think about this, because there is a long way and a short way to do with working out the area in this question. The question says find the area enclosed by the function. So let's have a look. The area enclosed by the function in that interval, so we're between our 0 up to 4 pi. So we've got basically 4 areas. We've got between 0 and pi, which I've called area 1, between pi and 2 pi, which I've called area 2, between 2 pi and 3 pi, which is area 3, and 3 pi and 4 pi, which is area 4. That gives us 4 separate areas which are identical. So what I'm going to do is I'm going to find the area of region number 1, and I'm going to multiply it by 4. Now what I also want you to think about in here, and I've crossed it out up here, under my integral, I do not want to do this. I do not want to find the integral between 0 and 4 pi of cos x on 2, because that would give me a value that is equal to 0. Remembering what our integration sign does, it actually cancels above and below the axes. So these two above the axes would be cancelled out by these two that are negative of equal value below the axes. So it says area, so I'm not integrating between the whole 0 to 4 pi. I'm actually going to integrate my cos x on 2 between pi and 0, and I'm going to multiply my answer by 4, which I will do right at the end, way down here. Okay, gives me 8 units. So let's look at that. So we are going to differentiate x on 2 to get a half. I'm going to divide by that half, and then I'm going to look at what happens when I integrate cos. I get sine, my x on 2 goes back in between pi and 0. 1 divided by a half is 2, so I end up with 2 sine x on 2 between pi and 0. When I pop my pi and my 0 in, I get 2 sine pi on 2 minus 2 sine of 0. Pi on 2 is 90. Sine of 90 is going to be 1. 2 times 1 is 2. Sine of 0 is 0. 2 times 0 is 0. So I get 2 minus 2, which is 2 units squared. That is not my answer. That is the answer for region 1. And I'll pop that in there for us to note. That is the area of region 1. The total area is 4. Look at that little bit there. Is 4 lots of those 2 units squared to get 8 units squared. Okay. Similarly, if you did not see that, we could have integrated our 4 regions, and we could check that, and we would get this value, that if we were to integrate region 2, that would be between 2 pi and pi. Region 3 would be between 2 pi and 3 pi, and region 4 would be between 3 pi and 4 pi. Each of those would be 2 units, which would give us 8 units. But that would take a long while, so we're always looking at shortcuts and looking at symmetry, and we can see that that's symmetrical. Okay, next curve. This one's fairly long. This is a difficult one, and one I really would like you to concentrate on having a go at and working right through to the end. Finding the area between the curves y equals sine of x and y equals cos of x in this interval only, pi over 4 and 5 pi over 4. So if we were to work out where these two graphs intersected, that is where they would intersect, and here's a diagram below, pi over 4 and 5 pi over 4. Now, you need to figure out which curve is which. Now, we know cos starts at 1, sine starts at 0 when we're on the y-axis. So cos is that curve that moves along this part here. So in the interval pi over 4 to 5 pi over 4, cos is our bottom curve. Sine starts at 0, sine is this top curve. So in the interval, sine is above cos of x, sine of x is above cos of x, so we need to do sine of x minus cos of x in that interval, because it's the above curve minus the below curve within that range of x values. So we're going to integrate that. When we integrate sine of x, we end up with minus cos of x. I've got that down there. When we integrate cos of x, we get sine of x, and we have a minus in the middle there, and we've got these regions that we're going to pop in there. So this is where we're going to have some mistakes happening. That was fairly straightforward, I think. Popping our values in, I've just popped my 5 pi and 4 into each of those. As you can see there, take away what I get when I pop pi over 4 in there. Now, you know I don't like working in radians, and I like you to think, if we can, in terms of degrees. So I'm going to change my 5 pi over 4 to 225, which if you need to stop the video and do that, please do that. And change my pi over 4 to 45. Okay, if you're stuck, I'll quickly show you then. 5 pi over 4 is 5 times 180 over 4, which if you calculate that is 225. That's where it comes from. Okay, now, that's the pink part. Now, there's a little bit of debate I've had with students over this before when we've gone back into year 12 and we've forgotten some of our year 11 work. But you need to think about 225 and cos and sine of 225. They are going to come up with negative values. So if you were to pop cos of 225 on your calculator, well, let's just do that for interest's sakes to have a look at it. Let's get my calculator sorted. So cos of 225 gives me a negative value. Now that is not that negative value that's already there. We've got another one that we're popping in there. So whatever you get for cos 225, it needs to be negative. Now I've got in one of my classes, there are kids that can recognise that 0.707 is a significant number, and it's 1 over root 2. If you can do that, well, you've kind of got a little bit of advantage, but we're not, I'm going to assume we don't do that because I don't do it like that. I'm going to go to my triangles, and I'm going to go to my illustrations to central. So I've got cos of 225. I'm over here. Here's my illustrations to central. I've got all our angles written around. Cos of 225, or 225, sorry, would sit in there. That's 225 degrees. So remember when we're working in illustrations to central, we're looking at what the equivalent first quadrant angle is. So what's 180 minus something, or sorry, 180 plus something that's going to give me 225? I want to know that angle in there, what that theta is, and that's 45 degrees. So cos, whoops, just fix that up there. Cos of 225 is equivalent to cos of 45 degrees, but in that third quadrant, tan's the only positive one, so it's going to be a negative answer, and that's where my negative comes from. Now, I want to work out cos of 45. 45 is a significant angle on our special triangles, so over here, we want 45 degrees. Cos is going to be 1 over root 2. So what we're going to end up with there is a minus 1 over root 2. So that's where if you can actually see straight up that that value that I had on my calculator there is 1 over root 2, that could come in handy. But I don't want the decimal format of it, so I need to get you to put it back into 1 over root 2. Again, I don't do it that way. I don't recommend it, but I know some people do. Okay, so I had my minus already. There it is. That's that minus there. I'll fix it up. That's that one. This minus belongs to the cos of 45, which is going to give me the 1 on root 2. The minus and the minus gives me the plus. I had a minus. but something's happened there. I've got cos of 45. In that third quadrant, like cos of 45, I end up with minus 1 over root 2 for that. So I get a minus and minus 1 over root 2. I get a plus 1 over root 2. So just be really careful with that. And if you need to pause that video and reassure yourself that that's the case, please do so. Next step, that minus stays there. Minus cos of 45, the minus stays there. Cos of 45 is 1 on root 2. Minus sine of 45 is 1 on root 2. So I'm going to put that minus out to both of those brackets. So I get 2 root 2 plus another root 2 plus another root 2. I have 4 root 2's. Now I do not want to leave my answer with a root on the bottom. I want to rationalise that denominator because that's now having an irrational denominator. So I'm going to rationalise and times by root 2 over root 2, which gives me 4 root 2 over the square root of 4, which is 2. 4 over 2 is 2. So 2 root 2 units squared is the answer that I want for that.